Okay, so we jump to question 2. We have a multivariable function from R2 to R defined this way. State and justify the continuity domain of f. So outside 0, the function will be continuous, since it is a rational function, right? And all rational functions are continuous. So we have to check continuity at point 0. Okay, so f of 0, 0 will be 0, and we have to take the limits here. Okay, so f of 0 is 0. No, not this. F of 0, 0 is 0, right? This is a function from R2 to R. Okay? Now this is the function. So the limit, if you take the limit, that will be 0, 0. We get an indeterminate. Okay? So since we get an indeterminate, we are going to check the limits using one direction, the lines direction. Okay? So that will be x to 0, right? We are going to change y for mx. X to the power of 3, x squared, mx to the power of 2. This is okay. So that will be x to the power of 3, x squared, 7 m squared x squared. That's okay. We factor x here, right? So we do limit when x goes to 0, x squared times x dividing 1 plus 7m squared x squared. We factor x squared, okay? And we cancel, and we get this. So limit when x goes to 0, that will be 0 dividing this, so that's 0. So this is not showing that the limit is 0. We took only the line's limit, right? And we got 0. So if there is a limit, the limit will be 0. So here we have to use delta epsilons, right? Okay, or take the limit under the definition. Okay, we're going to take delta epsilons. So for all delta positive, there is a epsilon positive such that, since this is to 0, x squared plus y squared square root minus then epsilon means that the function minus 0 is delta. So this is not my work, this is the student's work. I think this must be better than mine. So this is the absolute value, smaller. Well, yes, this is correct, since they are dividing by positive value. If we do not divide, we are majoring here. Right, that is correct. Well, yes, so this will be a upper bound, right? Because we are not dividing by something positive, okay? And so the students decided to do absolute value of x. Oh, okay. Okay, yes, since this is this, right? Okay, this is a upper bound, right? This times this, right? And since this is epsilon, each one of this is epsilon to the power of 3. So that's epsilon to the power of 3 minor than delta, right? So epsilon is smaller than the cubic root of delta. And it proves that the limit is 0. So f of 0, 0 is 0. and the limit is 0, so the function is continuous. Okay, so we just proved that and justified that the function is continuous in its domain, in 0 and outside 0. Okay, this was done, I think. Okay, show that f is not differentiable at 0, 0. Okay. Okay, let me consult something here quickly on the internet. So we have the concept of differentiability for functions of two variables. So a function f of xy is differentiable at a point AB if there is a linear function, that's why they write L here, such that the point plus m and n will be the partial derivatives, such that if the error E is defined, so they define the error, okay? And now the error dividing the square root of h squared plus k squared has to be 0. Or as I say, if there is no error when we subtract the function, the linear function, and our function, if there is no error. If there is an error, the function is not differentiable, okay? So the function f is differentiable on the region R if it is differentiable at each point of R, okay? And of course, informally, f of xy is differentiable at AB if it is well approximated, yes, by a linear function near that point. And if f of xy is differentiable, then the partial derivatives must exist. Yes, we will see that. Or we can see that right now. Here you are, partial derivatives and differentiability. If f is a differentiable function with a local linearization, that's what we call it, or a tangent, okay, I like to call it the tangent. If the f is differentiable with a local, okay, if you look well here, you have a tangent plane, but that's another story, okay? And m is the partial derivative of x, and n is the partial derivative of y. And then a very nice proof is showed here, okay? It's very well done, all this. And of course, if it is differentiable, the partial derivatives, they must exist, okay? Being differentiable means that the partial derivatives exist. Differentiability implies existence of partial derivatives. So one of the usual ways to prove that a function is not differentiable is to use the error, okay? You take this limit, and if you get 0, the function is differentiable. If you don't, the function is not differentiable. Okay, so we just saw that f is differentiable at x equals 0 if we have this d of x is equal to f at point A plus mx minus a. Okay? Now, f of x will be equal, so that's a function, to this d of x plus the error. Okay? And this will be a sort of a approximation error. Now, in our case, we have f of 0, 0 plus the partial derivative at 0.00 x minus 0, since everything is on 0.0, plus the partial derivative point y in 0, y minus 0. That has to be equal to, we'll check that in a sec. And then we take the limit when xy goes to 0, of the function f of xy minus, and we have, so if the function f has a derivative, this has to be 0. Okay, if this is not 0, that means there is no, the function is not differentiable. Okay, I think this is clear. So, okay, so in our case, f of 0 was 0, right? Let me read. Yes, f of 0 is 0, and now we have to take these partial derivatives. So f of 0 is 0. The partial derivative to x is 1, so that will be 1 times x minus 0. This will be 0. So this will be 0 plus x, right? So this will be x. So we have to put x here. We have to calculate this limit with x here. Okay? If we get 0, the function is differentiable. If we don't get 0, the function is not differentiable. So we are going to check the error. Okay? We are going to check if we get 0 or not. So f of xy will be f of ab, that's 0, 1, 0. So we have the error will be the function, right? This is already divided by x squared plus y squared. So limit when x and y goes to 0, the function x to the power of 3 dividing this minus 0 plus x plus y. Yes, this is the limit. Okay. Here we got already to the conclusion that it is not 0, but we have to check that before. So here we got the common denominator, right? X squared plus 7y squared multiplying minus x here, right? Minus x, common denominator, and this multiplies this one. Okay? So we got here so minus x times x squared, x to the power of 3 minus x to the power of 3, they cancel, right? We get minus x to the power of, I don't know why I wrote this. Okay. Oh, okay. And now, yes, we get this. That's the limit. Okay. Now we have to check if this limit exists. And we are going to take the directions, the line directions, right? Okay, we will replace mx in the function, so minus, this is only x to 0, right? Minus 7x to the power of 3, x squared. Where there was y squared, we replace by mx, so we get m squared x squared times this. We get here, that's the same as square root of absolute value of x. So that should be x, that should be plus or minus x, right? But that's not going to change anything. So there should be a plus or a minus here, but it doesn't matter here. So x times all this, that will be x to the power of 3. We factorize x to the power of 3, and there is a huge confusion here, right? So we factorize, and we got what? We have limit when x goes to 0, that will be x plus and minus due to this absolute value. But so this one cancels with this, right? So we'll have minus 7 dividing 1 plus 7m squared, right, times square root of 2. Okay? So the limit depends on m, so the limit is not 0. So this means that the function is not differentiable at 0, 0. Okay, so show that f is not differentiable at 0, 0.